Hi everyone, now we will continue electrical energy in the capacitor when you store a charge in it. So it's given by potential energy 1/2 times Q times V, and you can replace the Q with the C times V, and you reach this representation or presentation. Or you can replace with V with Q divided by C. Q times divided by C. Now I replace the V with Q divided by C. Now we have 1/2 Q squared divided by C. So you can ask where this half comes from. Actually, this is one of, you can see it in the physics a lot, like in the kinetic energy. And for example, in here we have 1/2. Actually comes from like I will show that in normal simple examples. If in any potential, if you bring, for example, we had the plates, right? We had parallel plates, and if you have a point charge, if you go from, let's say, 0 volt to 1 volt, the energy gained or potential energy gained by charge is going to be just delta V times Q, right? And in the capacitor, let's say you have some charge, let's say you have charge Q, and the potential is going to be Q divided by C. Or if you plot this way, you will see linear relationship between the potential difference and Q, and that's proportional to C, right? As you increase the Q, you get more voltage. Let's assume you have some potential at certain point and charge, and in this one, the potential is going to be, let's say, V, and charge V naught, and the charge is Q. So let's say you add a little bit of charge, delta Q. Now the potential is going to also increase by delta V, delta Q, right? So, and in this case, when as you, and the work done by, in like the potential increase is going to be delta Q times V. Like you are making this mass, this much, with the area of this region, right? Because this is delta Q, this is delta Q, and the potential is this. So, and as you add more and more charges, and if you think you started from 0, the energy is going to be the area under this triangle. So then at the end, if you find the total charge, total energy, or total area of this triangle will be total V times total Q and divided by 2, right? That's how you approach it mathematically. In other way, for example, you can think at the beginning, you don't spend too much energy, like, because there's not much charge in the capacitor. So, but as you add more and more and more, you spend more energy to add more charge. So that's why you have that 1/2 coefficient in the energy. And let's say in the space, you have a certain electric field. that means you have electrostatic energy in that space, and the energy density is given by this 1/2 times epsilon naught square of electric field. So if you apply this into capacitor, let's say the potential energy of a capacitor is 1/2 C times V square, and 1/2 is, this is C, capacitance, and the potential is E times D, and you take the square of the V, and if you change the location, I mean rearrange the electric field and area and etc. Now you see you have E square and D square. Now you have only 1D multiplication, and the area comes from the capacitor. You have epsilon naught and E square. So now A times D is actually the volume of the parallel plate. So it's the area and the distance. The volume is going to be A times D. And this is the energy density. When you multiply the density with the volume, you will get the total energy. Okay, that's all for the energy of the capacitors. And one important thing you to be careful when you have when you see a capacitor in a circuit, it may be full of charge, so it can have enough charge to give shocks. So, and also can be dangerous for the equipment if you just discharge the charge by touching the capacitor on a circuit. I mean, it's not good for you, and it's not good for the device. So be careful when you see capacitors on certain circuits. Okay, let's do some examples about the energy of the capacitor. Now, in the first one, calculate the Q naught and the total energy. The Q is going to be V times C, 120 volt times 8 microfarad. It's going to be 960 microfarad, or 0.96 or coulomb, sorry, millicoulomb. And the energy is going to be 1/2 times C times V square. So it's from the previous pages, you see you can have 3 different versions of the energy, right? 1/2 Q times V, or 1/2 C times V square, or you can have 1/2 Q square divided by C. So depending on what you need or what you have, you can use any of them. So I don't have voltage, I'm on Q, and like here, like I have V and C, I can directly put it that 1/2 8 microfarad times 120 square. So this is going to be 600 microjoule. The energy unit of the energy is joule, and 7.6 millijoule. Then the question continues: disconnect C1 from the power supply and they connect to C2 with no charge loss. So in the B part, we connected the C2, the 4 microfarad. This was 8 microfarad. Now, without losing any charge, so what is the final charges and potentials and energies? Now, what you see is when they are connected, you have two options. You have one options, but you can do you can do two ways, and one is correct, the other one is incorrect. So the first correct way is of just when you look at it, assuming they will have the same potential, because these are connected on the same cables, right? So the cables, when they have a different in potential, they will flow the charge. So now they don't have the potential until they have the equal potential, they will exchange a charge. When they finish exchanging, they will have equilibrium and they will have the same potential. Don't assume they have same charges, okay? They will not share the charges equivalently. So at the end, you have same voltages, Q1, C1 must be equal to Q2, C2. But you know the total charges conserved, right? Q1 plus Q2 must be Q0, right? Because they will conserve the charges. And what we can do is Q1 and C1 is 8 microfarad. Q2 is 4 microfarad. Now you can simplify. Q1 is going to be 2 times Q2. So you can also think about the capacitor of the C1 is 2 times larger, so it should be able to hold 2 times more charges, right? And Q1 plus Q2 is, we know it, 960 microfarad. And I can plug the here, Q1. Then Q2 will be 960 divided by 3 microcoulomb, sorry. Q is charge, not the capacitor. Now, if you divide by this, it's going to be 320 microcoulomb, and Q1 is going to be 640 microcoulomb. And the potential for these devices, Q1 divided by C1, you can use any of that. 640 microcoulomb divided by 8 microfarad, it's going to be 80 volt. So you can do the same thing with the Q2 if you want to double check. 320 microcoulomb, 4 microfarad, 80 volts. Okay. Then it asks about what's the total energy. Then we can do two ways. First, capacitor will have Q1, 1/2 Q1 times V1. And Q1 is 640 times V1 is 80 volt. And E2 is going to be now you see that if you look at the E1 and E2, and the summation will be less than the total energy. So during this process, we lose some energy in the system. So you have two capacitors in another example and 12-volt battery. Do you need to connect them in series or parallel to store maximum energy? Now let's forget about the Q. Let's use the one with just capacitor and the potential. Now you have a constant battery, right? Your goal is to maximize the energy. So energy is proportional with the capacitor. So you would like to increase the capacitor. To increase the capacitor, you need to connect them in parallel.